All right, welcome to Section 3. Section 3, we're going to be looking at two different related topics. The first just being a very general derivatives of inverse functions. So over on the left here, we have the f of x equals x cubed. Taking its derivative, in other words, the slope of this curve, we would get that f prime of x is equal to 3x squared. Well, if you remember, when you're taking derivatives, to do a derivative, or I'm sorry, to take an inverse, you would switch the x and y's, and then solve for y, change back into our function notation. So the inverse of x cubed is the cube root of x, or x to the 1/3. Well, if we take the derivative of this, x to the 1/3, we're going to get 1/3 x to the negative 2/3, which is 1 over 3 cube root of x squared. Well, in terms of our x and y notations, this would be the same as saying 1 over 3 times y squared for our inverse. Now, if we see, this is very similar here to what we got as the derivative of our original function. And what this means, the only difference we see is that here we have a 3x squared, and here we have 1 over 3y squared. So they're almost reciprocals. The difference being this is an x squared, and this is a y squared. And so what we can say, and we really can say this, is that the slope of the inverse is the reciprocal of the slope of the function. The reason that our variables are switched is it goes to what happens when we find inverses. And that's just remembering that x and y switch for inverses. And that right there is typically the most difficult part when dealing with derivatives of inverse functions. Is, yes, the reciprocal part for the slopes is very easy to remember. It's remembering the x's and y's have to switch also. Now, a lot of the times we're not actually going to be finding the inverse function. By using this trick of reciprocal slopes, for inverses, we actually can do a lot of work with an inverse without ever knowing what it is. So one of them being, we know if an inverse is differentiable if the original function is differentiable and if the original function's slope is never 0 in that interval. So here's an example. Let's say the function is x to the 5th plus 2x minus 1. If we plug 1 in for f, 1 plus 2 minus 1 is going to give us 2. So I know that the point 1, 2 is on my graph of f. Well, for an inverse, because the x's and y's switch, that means the point 2, 1 must be on the graph of the inverse of f. And this is one where trying to find the inverse of f would be quite painful because we'd have to have y to the 5th plus 2y minus 1 where we're trying to isolate y. So let's say we want to find the derivative of the inverse when x is 2. Well, instead of worrying about actually calculating the inverse, we can deal with the function in that we can say, well, I know this is going to be 1 over the derivative of f, but I have to pay attention now. The 2 I'm plugging in on the derivative of the inverse, that's an x on the inverse, which means that this is the y value for when I'm dealing with the slope of the original function. Well, y was 2 meant x was 1, so the derivative of the inverse when x is 2 is the same as 1 over derivative of the function when x was 1. Well, for us, f prime for the original function was 5x to the 4th plus 2. Well, when I stick 1 into that, I would get 7, so derivative of the inverse when x is 2 is going to be 1/7. slightly different take on it, but still similar idea, is here our function is cosine x plus 3x. Again, a function it'd be difficult for us to find the inverse, but because slope of an inverse is the reciprocal of slope of a function, we don't need the inverse to talk about the slope of the inverse. So if I find f of 0 here, well, f of 0 is going to be, well, cosine of 0 is 1 plus 0, so this is going to be 1. This means that we have a point 0, 1 on our graph. Now for f prime of 0, we first need f prime, which would be negative sine of x plus 3. Well, I plug 0 into that, that'd be negative of 0 plus 3, which is 3. Well then, the inverse of 1, remember, this means that x is 1 on the inverse, so y is 1 on the function. And for us, that occurred when, on the original function, that meant x was 0. On the original, so that means that's the y value here, because x's and y's are switched. So that means when we're dealing with the derivative of the inverse, when the inverse is x is 1, that's 1 over the derivative of the function, when the y value is 1 on the function, which meant 0 for the x here, which we already found that was 3, so this equals 1/3.